In this video, we are going to discuss an ideal heat engine cycle that is called the Carnot cycle. This, as I said, is a theoretical cycle which lays the foundation for pretty much all heat engine cycles. So let's see if we can understand the fundamental principles of Carnot cycle here. So what you see here is a schematic of a heat engine cycle. Let's assume that this is working based on a Carnot cycle. So what you have here is a heat source at temperature of T1 that transfers a heat of Q1 to this heat exchanger here. So a heat transfer of Q1 happens here, and the heat exchanger delivers a working fluid at temperature of T1. So you have a working fluid flowing at a temperature of T1 to the turbine here that produces a turbine work from this temperature and pressure of this working fluid, and thereby the temperature of the working fluid changes to T2 here. As it leaves the turbine, the temperature changes to T2, and then you have another heat exchanger that is operating at a temperature of T2 and discharges a heat of Q2. Let's say this is Q2 to the sink. This is a heat sink or a heat. This absorbs the heat from the heat exchanger, and the sink is at a temperature of T2. Obviously, the heat is discharging to T2, and therefore the T2, the temperature of the sink, is lower than the temperature of the source, i.e. T2 less than T1. And then the working fluid is pumped back to the heat exchanger using a pump work of WP. So the pump is doing its work to increase the pressure of the working fluid from the level at 2 to the heat exchanger 1. So you have a station 3 here and station 4 here. Now let's see if we can draw the pressure, volume and temperature entropy diagrams for this Carnot cycle. Basically, this is a heat engine that is producing turbine work, consuming Q1 of heat energy and WP pump work, and releasing the Q2 heat to sink. So it absorbs heat from source T1 and it releases heat to sink T2. It also absorbs pump work at pump in between station 3 and 4, and it generates a turbine work of WT between 1 and 2. So let's see if we can draw the pressure, volume and temperature entropy diagrams for this Carnot cycle. I made it easy for you by drawing the diagrams in advance. So what you have here is a process from 1 to 2 that is absorbing the heat at Q1. So you have, sorry, the diagrams here is a little bit wrong. Instead of 4 you have 1 here. This is incorrect, and that is 2. After the heat exchanger you have 2, and after the turbine you have 3, and after the heat exchanger you have 4. So 4 to 1 is the pump. So let's see. So from 1 to 2, this is absorbing the heat, 2 to 3 generating the turbine work, 3 to 4 releasing the heat, and 4 to 1 increasing the pressure by absorbing the pump work. Now these two processes 1, 2 and 3, 4 are isothermal processes. So these are reversible isotherms. What is a reversible isothermal processes? Isothermal process is one where the temperature remains constant. So you don't increase the temperature in adding heat from 1 to 2, or you don't reduce the temperature from taking away the heat from 3 to 4. So how does that really happen? That is the clue here. That is the reason why this becomes a reversible process or an ideal engine cycle. 2 to 3 and 4 to 1 are reversible adiabatics. So these are reversible adiabatics. An adiabatic process is one where there is no heat transfer, only work transfer happens. So there is no heat transfer when the working fluid transfers from 2 to 3, and there is no heat transfer from when the working fluid transferred from 4 to 1. To make things easy, I can give you an example. Let's assume the working fluid is water. Okay, we are all familiar with water, and most of you will know the characteristics of water at different pressure and temperature. You might not know that water can coexist at two phases at the same temperature. At 1 bar 100 degrees C, water, otherwise H2O, has two phases. It can exist as water and it can also exist as steam. This is called a saturated state. So what is the condition of a saturated state? Water at 1 bar 100 degrees C can be converted to steam at 1 bar 100 degrees C just by providing heat. There will be no temperature increase, and the process from 1 to 2 can be considered as converting water at 1 bar 100 degrees C to steam at 100 degrees C. There will be a slight decrease in pressure because you expand the volume. Water changes to steam, therefore there is a volume expansion, so pressure will be reduced slightly, but the temperature will not change. And the heat addition in that process is called the latent heat addition. Because there is no temperature increase, you can only sense the heat addition by some other measurement. You cannot measure temperature and say there is a heat addition. It is latent, it is hidden, there is no temperature increase. So it is called latent heat addition. So let's assume that we are using water at 100 degrees C here at 1 bar and heat it, provide the heat and convert it to steam at a slightly low pressure at 100 degrees C. It is completely converted to steam at 100 degrees C. Now you are going to produce that, provide that steam to a turbine, and by doing that you take the energy of the steam at whatever pressure it is and use that pressure to do some work on the turbine or rotate the turbine leaves and transfers the working medium from, i.e. the steam, from 2 to 3. So the turbine work is done. Obviously, by traveling from 2 to 3 or changing from 2 to 3, you lose the pressure. So if the water was at, say, just under 1 bar here, it is at 0.8 bar here. Oh, sorry, the steam was at just under 1 bar here. Let's say it was at 0.8 bar at station 3. Now at 0.8 bar, steam does not need 100 degrees C to remain as steam. At 0.8 bar, steam is only needs say 80 degrees C to remain as steam. And from here you remove some heat. Again, it's latent heat, so there is no temperature reduction. So whatever the temperature you had here will be the same as at this point. The temperatures at 3 and 4 are exactly the same. And therefore you have lost some heat and changed the phase from steam to water by transferring the working fluid from 3 to 4. So you have a saturated water at this stage, at whatever pressure it is at. Now you need to compensate for the pressure loss from 2 to 3 by pumping this working fluid from 4 to 1. So you add some pressure from the pump and the working fluid is transferred from 4 to 1. Again, there is no heat transfer. This is an adiabatic process, so there is no heat transfer. Working fluid is just transferred from 4 to 1 without any heat transfer, and by transferring from 4 to 1, the pressure of the working fluid has come back to the original pressure at 1. Say it was at 1 bar. So this process from 1 to 2 and 3 to 4 are heat transfer processes, but there is no temperature addition. And the processes from 2 to 3 and 4 to 1 are work transfer processes, but there are no heat transfer. And therefore 1 to 2, 3 to 4 are called reversible isothermals, and 2 to 3 and 4 to 1 are called reversible adiabatic process. This is the PV diagram of Carnot cycle, and you also have the temperature entropy diagram here. And as I said, from 1 to 2 there is only heat addition, no temperature rise, and therefore T1 is equal to T2. And from 2 to 3 there is only work transfer and no heat transfer, so there is no entropy change. Entropy remains the same. Entropy will only happen if there is heat transfer, so S2 is equal to S3. And then again, the transfer from 3 to 4 is an isothermal process, and therefore there is no temperature change. In other words, T3 equal to T4. And from 4 to 1, it's a work transfer without any heat transfer, and therefore the entropy remains the same at 3 and 4. S3 is equal to S4. So you have two reversible isothermals and two reversible adiabatics. These four processes constitute a Carnot cycle. And because there is no heat transfer here or here, whatever heat is transferred into the system will be equal to whatever work is transferred through the system. There is no work transfer here, only heat addition in these two processes, and there is no heat transfer here, only work transfer in these two processes. And therefore we can say the net work of a Carnot cycle is equal to net heat transfer. That is, turbine work minus pump work will be equal to Q1 minus Q2. We will look into detail. We will continue this discussion on the Carnot cycle in the next video. There are a few more things that I need to bring to your attention, but have a thorough understanding of these processes. Make sure you look through the pressure, volume and temperature entropy diagram, and there is a lot connected in the study of thermodynamics if you get a good understanding of the Carnot cycle. Once again, thank you for watching. Keep watching, and if you have any comments, please feel free to use the comment box. Thank you very much.